good morning, good afternoon, I suppose good evening, depending on where you're joining us from today. My name is Chad Schmitke. I lead the development team for MapleSim at Maplesoft, and I'll be talking today about how our customers are using our roll-to-roll web handling library in the converting roll-to-roll industry. Okay, my outline is actually pretty simple. I'm just going to start with who we are, just a very brief update on our company, talking a little bit more about what we do and our libraries to give you an idea of how Maplesoft interacts with their customers. Then answering what I think is the key question here, why would we be using simulation in the roll-to-roll world? And don't take our word for it, but how are our customers using it? So first of all, who we are, very quickly. We started off actually right here, and I say here I'm speaking from Waterloo, Ontario, Canada, as a research company in the early 80s, and we've since grown to be a global company selling our both academic and professional software worldwide. We have an engineering solutions group that primarily use the Maple and MapleSim pieces, and I'll be talking about MapleSim primarily today. So what do we do? So we're a software company, but our key mission is to come alongside our customers and help them build better machines and solve complicated issues faster. And we do this in two ways, but primarily it's by providing software that allows them to model their ideas of real-world systems or their real-world system that they have in the computer, where they can ask questions of it, where they've got full insight and information into it. They can, if there's a vibration they want more details on, they can see what that frequency is. If there's a tension, they can see the value of the tension. But also they can rapidly change the model and again ask those questions quickly so they can try out different designs. So there's a software side, but as I said, we also have an engineering group, and they'll come alongside and they can build models for people. They can also do analysis on models for our customers or provide training to do either of those things. Now, on the right-hand side, you can see a bunch of pictures. There's satellites, there's a car, there's an excavator there, a print machine. They are pretty pictures, and they make the slide look nice, but also they speak to the different areas that Maplesoft services and where we have helped customers do exactly what I've talked about. And I want to spend a little bit of time actually talking about some of the libraries developed in those other domains to give maybe confidence and understanding about the kind of company that Maplesoft is. The first one I want to talk about is our heat transfer library. Most of our models or our libraries are multi-body or some actuated multi-body. But here we came along customers who were looking for a tool to stand in the gap between fast system level simulation and slow, detailed FEA simulation. And so in talking back and forth about how they could model the transients, looking at the research and talking to our customers, we developed a library that exactly fit the kind of work and problem that they were wanting to do. It's how that and now if you buy MapleSim, you have access to a heat transfer library that came about because we work closely with our customers trying to solve the problem. The same is true for our hydraulics library. We had in a base offering, but we had a customer with an internal tool. And that tool had a level of fidelity they wanted to match, but they wanted greater speed. And so again, came alongside, working with the equations, working with the customer to build the library, and in our case, extend our hydraulics library to match the needs that they were telling us. Our pneumatics library, again, this is useful in roll-to-roll because if you actuate a dancer with pneumatic cylinder, no problem, we can handle that. But it's an example of taking a technology like what we built for the hydraulics and extending it to the pneumatic domain. I include ropes and pulleys, one, because I actually really like the inverse kinematics going on there, but two, because it's an example of where we built a library actually from our own interest side, thought we could apply it to the web handling world. 5 years ago, we were presented by a customer on the web handling side, and they said, hey, you've got, we said, we've got ropes and pulleys, maybe there's something we can do here. But in doing further research, there's a lot of information published by Oklahoma State University, the Web Handling Research Center there, that was made public. But also in working with customers, found out that it's not quite the right dynamics that you're dealing with inside of ropes and pulleys. And as a result, the web handling library was, or the idea for it was born. And 4 years ago, we released, well, be 4 years in fall, we released this library. Now, this library, as I said, was developed based on the research from Oklahoma State, based on work with customers and their machines. But since that time, it's been validated against many, many customer models. I'll be talking about that at the sort of latter part of this presentation. And I've started to list here some of the things that you can do. You can investigate slippage. You can see disturbance propagation. You can see tension control. You can investigate how eccentricity can affect your model. There's a whole host of things that our library can do. And actually, this isn't the complete list either of the things that it can model. Air entrainment was added just in the spring of this year. And our own customers, some of them have extensions to the web handling library that we've built for them because they have a particular dynamic that they're interested in and they've invested their IP in it. So it's a custom library we've built for them so that they can tack that into the web handling, the standard web handling library that you would get if you buy MapleSim. So I talk about this library, I show these things. These are all things that you can simulate, but perhaps backing up slightly, it begs the question, why do you care about simulation anyways? We've been doing simulation in all those different areas I talked about, but why do we care about adding simulation to the process? How does it help us solve the problem faster? And maybe the way to answer that question is by looking at a problem to start with. So we've got a printing machine here. That's great. What kind of problems do engineers often get faced with in the R2R converting world? Well, often they might be asked for a new design. Maybe it's a brand new design. We're working in your company wants to change an area it's working in, but more often it's a design or it's a modification to a machine that already exists. This usually comes about or can come about because environmental standards or something has changed and a new material is being fed through the machine that the machine was not originally designed for. And so engineers have to figure out how to deal with the problems that come out from that. Or maybe it's not that a new material has been in, there's been some wear, or it's a machine and you're trying something slightly different and there's quality issues, there's tearing, or there's wrinkling, or there's some sort of vibration that causes those things that engineers are trying to deal with. And I laugh at the last one, which is someone needs it to run faster. If you didn't have quality issues before, once someone wants it running fast enough, quality issues will appear. And in all these cases, the engineers are told, hey, I've got a problem with my machine. Can you solve it? And the engineer has to go off and think about where they think the problem's coming from. And they come up with a design, something they think could solve the problem. Well, of course, they can't just say, I've got it solved. They've got to go and implement it. So a technician gets involved, you modify the machine, you do a run of test runs, you put some material through the machine, hopefully nothing flies across the room, and you look at the results. And those results are maybe you're just watching it to see if the problem's gone away. Maybe it's something you have to wait over time to see if the battery quality has improved. Maybe it's something that you got a load cell somewhere and you're trying to see if you can see the fluctuation going down. But if it doesn't solve the problem, you start this slow process again of doing this testing. And of course, there's challenges, right? There's never enough load cells to give an engineer a full picture of what's going on with the machine in the first place. Load cells are expensive to add to machines, but also there's some areas of the machine you just can't add them. And not only that, but every time you run one of these tests, you lose material. And in some domains, the material is not that expensive, but certainly in battery handling, those materials can be quite expensive. And so you lose that every time you run one of these tests, and that can add up. Outside of the material loss, there's the time required for engineers. Your engineering team is focused on it. You've got technicians who are working, modifying the machine, getting their analysis and sending it back to the engineers. All of that is time that could be spent on other problems that you should be investigating or need to be investigated. And of course, there's the machine time. And hopefully that machine isn't in production, because if it is, you also are losing actual production time while you're trying out your tests. So what does software offer to this kind of a scenario? The big idea behind software is that you can replace the physical machine with a virtual machine. And now you can start running these tests on the model, on the virtual machine, rather than on the physical machine itself. And of course, if you're running on a virtual machine, you don't have problems with load cells or information. Your engineer has the full picture of the tension and the interplay between the controller and the machine. They also, there's no loss of money because you're not obviously using material when you do a test run. You don't have a whole bunch of people who have to modify a machine and get results back. So you're saving people's time. And you obviously, none of those virtual machines are going to be in production. Now, I'd love to say that is the full story for software, but it's not. In reality, you do a combination of the two things that we talked about there. So you've got the virtual machine running in the top, and you're doing fast iterations of that upper loop. So the initial ideas, the initial proof of concept tests, you can do very quickly on the virtual model. And then once you have something that you feel confident with, narrow down your different designs, you can go to the physical test and actually make sure it satisfies and solves the original problem. And one thing that happens here that I like to point out is that rather than, look, we're all busy and we're all pressed for time. So rather than just getting the first satisfying solution, because you can do those tests on the virtual side so quickly, you can compare different designs and actually choose the most robust of your solutions that solve the problem, not just needing to get the first one that worked on the physical test and move on. Now, a common objection, and a fair objection at this point, is what happens if you can't reasonably model some portion of the system. So I've got some examples. If you've got a web that's going through a bath, it's not the case that MapleSim software won't predict how the chemicals in the bath are affecting the web and how they're going to change, Young's modulus as it comes out. We're not going to predict that. We can model, different Young's modulus, different materials going through a system, but not predict how your chemical process will affect it. I had an engineer come up and he was talking to me about at a show, and he wanted to know if we could model. He had a laser that was cutting a web and he was getting a splatter because of the coating on the web. And I said, unfortunately, we can't model that. But in further discussion, it turned out that tensioning going into this process was really important. And so there were some pieces that the simulation could help him with, even though we didn't model the final detail of the converting or splitting process that he was interested in. And I think about that in a little bit like Sudoku. So if you're familiar with the problem, you've got these grids, and each of these boxes has to have the numbers 1 through 9. Every row and column has to have the numbers 1 through 9. And what you want to do is you have to make guesses because you don't have all the information. So you say, I think this might be a 2. And then you work things forward and see if all the rules can be handled, and you solve the problem. In cases where simulation doesn't answer all the questions, maybe part of your converting process, it can actually give you a leg up still, because you imagine, what if you started this Sudoku problem, but everything in blue you were able to very rapidly fill in with confidence. Now the parts of the model that you still don't know about, you still have to go investigate them, but you have a deeper understanding of the rest of the system, and you're going to go down fewer dead ends because you've already solved parts of the problem, or you understand it. So even in cases where simulation doesn't help you or can't solve the full problem, it can rapidly reduce the number of unknowns that you're trying to solve as part of the problem. Now, I can talk all I want about simulation, but let's talk a little bit about how our customers are using simulation today. And hopefully that'll give you more insight into how you could use it in your work. So this first case is one of roller eccentricity. A model or a machine was shipped to a customer. The customer assembled it, and it was behaving oddly. They were getting a tension fluctuation that was unexpected. Our customer wanted to do a proof of concept to see if they could identify this kind of a thing with a model. And so, sure enough, they were able to inject eccentricities into a model. They were able to introduce the same kind of failure their customer had, so they can say with confidence, it's this roller that's causing the problem, because we can reproduce what you're seeing in our simulation software. They now use this as part of their new line development tasks as they're investigating and building new machines. I should say here, and I didn't say it right at the beginning, the models I'm going to show are from our examples. Obviously, I'm not going to be showing customer models on the slides here. But we've tried to choose ones from our examples that are the same flavor of what we're talking about. Another use case, this one's really neat. You can imagine the shuttle that you see here going back and forth creates some interesting tension dynamics. A customer had already done this, they had analyzed the system, and they said, we want to see if the software can handle a challenging case like this. They did the proof of concept. They were able to match what they saw on the software, same patterns as what they saw on the real machine, and because of that, they had confidence to move forward with the simulation software for their subsequent design work. Here's another case that's similar, only in this case it was for buffering systems. They were looking at different styles or kinds of accumulators, so changing the number of rollers, the diameter of the rollers, and they wanted to use simulation to try and do this optimization. But they first wanted to do a proof of concept to validate that they could get the same kind of results that they saw in the real machines that they had tested. They did their validation, found that, and now they're using it to do that optimization that I was talking about. I really like this example because it ties back to some of the stuff I was talking when I was going through libraries and said how we built things. It ties back into this. This customer had an issue where they had a vibration problem they had been spending months trying to track down, couldn't figure out where it was coming from. With the aid of software, we're able to identify that it was actually coming from the winding process, from the winding roll, and in further investigation found that actually it was the the diameter of that roll was changing discretely because the material coming in had discrete changes in thickness. And so that was causing a vibration to get fed back into the system. So in order to simulate this inside of MapleSim, we had to build for the customer a new component, a winding drum that would allow this kind of discrete change in the diameter as it was winding up the materials coming in. So now if you start MapleSim today, you will find that we have that component. We built it working with a customer who was trying to solve this exact problem. So I like this model because it shows two things. One is the ability to do what ifs and analyze in software, but also our engineering team coming along and us extending our product to help solve the problems that our customers are seeing. This is an interesting one. This wasn't a machine that existed, but a customer said, hey, we've been doing web handling design for a long time, but we've never gotten into the Z folding area. And so they wanted to try that, but they thought they could use software to start to give their engineers a feel for how the different elements of the design could work together in a Z folding machine. And so they used it even for their initial prototype to figure out what size of motors and actuators would they need when they built their initial prototype, as well as, what kind of design were they going to work with. The last example I want to show here is just an interesting one that a customer had a phenomena they couldn't understand in their web line. They ran it one way, there was a slippage that was happening, but if they ran it the other way, it was nice and tight, and they couldn't explain why that was happening. Well, as I mentioned earlier, simulation gives you deep insight into all the things going on in your line. And I've got two pictures that show the exact tensions that were coming out of the machine depending on the direction of the web, depending on the web direction. They were able to use this to understand the relationship between the bearing drag or bearing losses and the tension in that line, as well as the controller that they were using. And that was allowed, that gave them the insight they needed to actually understand the problem and then solve it. And this is really what we talk about for what we provide our customers, right? We allow them to build better machines and solve complicated issues faster by providing them with software that can perform what-if scenarios and get all the information about the problem that they're solving. And then, as I said, and I think I've talked about it a variety of different times here, our engineering services team can come alongside and either provide training or actually do the work with the simulation, if that's something you need us to come alongside and do. So remember, key idea here is that what does software provide in the R2R converting world is it gives you that fast iteration loop that you can quickly try new ideas, see how they work, iterate quickly before you go to the more expensive and time-consuming physical tests. The goal here again is just to give better insights into better insights to your engineers, so engineers can build better machines faster. I thank you so much for your time today. And at this point, we can open it up and we can have questions on any of the things I've talked about or MapleSim in general. Thank you so much.
Thank you, Chad, for a really informative session. That's really neat to see how the simulation software is making quite a difference in the state of the industry at large in so many different segments. So again, we will open up the questions for if you have a question for Chad about MapleSim or any of the simulation applications, please type it into the chat and we'll read that out shortly. Chad, if you are available, just join up our stage, and we'll. Great, thank you. And so we'll just while we're waiting, or in case people are curious, a lot of what you showed seemed to be simulations that look quite complicated. They were parts of whole lines or quite complicated processes within the system. How much effort is required to start modeling? Because when people think of simulation, often they think of fairly complicated mesh 3D CAE systems, or like you mentioned, the finite elements that might be needed for material analysis. How does it compare when you're looking at the type of simulation you're working with?
Asking someone who heads a development team, how easy it is to build in your software is always a dangerous question. But let me break it down into a few different pieces. First of all, you don't always have to model the whole machine. Sometimes you just model between tension zones. If there's something you're interested in looking in, you can limit the scope of your modeling in that way. And probably the best way to answer the question about how much effort to get going is looking back to our customers. We've interacted with many over the last 4 years in the web handling R2R world. And to date, as long as there's been a component in our library for it, customers have had no troubles constructing their model. There's been a lot of emphasis in the design to say, hey, there's your SRAP, there's your roller. It's really like dragging over the pieces that map what you've got in your web line, connecting them, and then moving forward. The part that actually takes longer is getting the information for the web line. So what you need to build it, and actually if you stay on, Orang Vahid is going to be talking later on today about the process of building a model, but succinctly here, we need the XY coordinates of those rollers, we need the diameters, the inertia or material of those rollers. And as you put those together, constructing the model is quick. I think we can build a model in a day for a very large web line. But the process of getting that data is often what slows people down the most. Once you get it, building that nominal model, and I say nominal meaning a model that is a generic model for, so it's not specific to an exact machine, but is representative of that class of machine, is very quick. And once you have it, you can already start asking questions of it to get a feel for and understanding how tension propagates through a system. The time that sometimes takes longer is if you say, I want it to match an exact machine, and then you start a process of getting data off that machine and running the virtual model to match the data that you're seeing from the physical machine. But there's a process for that, and we can certainly walk people through it.
And the software itself is general enough in the sense of that it's customizable enough that it can actually adapt to the examples you showed were from very different applications, very different systems within customer environments. So it sounds like there's quite a lot of flexibility for an engineer who knows what they're doing. And as you mentioned later on the last session of the event, we have Orang Vahid, who will be walking through a little more detail about the steps and some ideas with ways that can be applied. So thank you. Yeah. Okay.
Yeah, just connected to that, you're absolutely right. There's flexibility there, and if there is a piece or a dynamic that a customer doesn't have, or there's something novel in what they're doing, because that happens. People have a different design or piece that sometimes we don't have in the library. That's something we can absolutely step in and extend the library for you. I mentioned during the presentation that some of our customers have custom extensions to the web handling library just for that exact reason.
Certainly. Okay. Well, thanks again, Chad, for your content here, and we'll move on over to our next speaker.
Thanks so much.